All right. Well, welcome back from spring break, class. I hope you were all able to relax a little bit. Um, so we're going to start this lecture reminding ourselves a little bit of what we covered last time. We've been discussing phase transitions. Over the next couple lectures, we'll be able to wrap up that discussion and move on to other questions of mass equilibrium. So let's first remind ourselves kind of where we've been. So we've been thinking about phase transitions in a very useful way to quantify phase transitions or, remember the kind of structure that emerges from phase transitions is to think about phase diagrams. An example of a phase diagram is one I've shown here, plotted in the pressure and temperature plane. Now for a common substance, two phases that might be exhibited in a pressure temperature phase diagram would be at, say, high temperature and low pressure, a vapor, at low temperature and higher pressure, a liquid. And we know what distinguishes a liquid from a vapor fundamentally is its density. So we could depict that low density vapor state in that way, and the high density liquid state through filling in that box there. So this phase diagram summarizes where under equilibrium conditions, which phase is stable. Namely, if I'm to the right of this line, I'm at equilibrium going to find a material in its vapor. If I'm to the left of that line, under equilibrium conditions, it is most favorable, most probable to find a state of matter in that liquid form. Now, last lecture, we discussed some dynamical implications of these phase diagrams and what it actually means to try to take a vapor and convert it into the liquid. And that discussion led us into a discussion of things like surface tension and the distinguishing features of different control parameters and how they impose different sorts of constraints on what phases we see. And so let's remind ourselves a little bit about that by thinking of the question, well, what happens if I take this vapor? I know that I'm going to find it over in that region of the phase diagram, or the liquid over in that region. Let's ask a simple question, which is, what do I see if I park myself exactly on that line? If I put myself directly in coexistence, controlling the pressure and the temperature, what do I see? Think about that for a second. And think about it in the context of the discussion we had last lecture. So the answer is that it depends, right? If I start in the vapor state and bring myself to that coexistence line, then if I put myself exactly at coexistence, exactly on that phase boundary, what I'm going to see is the vapor. And that's because, as we discussed, there's a huge barrier to going from the liquid to the vapor, or vice versa. And at coexistence, that barrier is associated with growing a macroscopically large interface, which is a huge free energy to overcome. On the other side, if I start with the liquid and bring it over into coexistence, the same thing is true. I have to overcome a very large barrier to turn into the liquid. And so if I put myself exactly at coexistence, starting from the liquid, I'll see the liquid on that phase boundary. Now, this is an important distinction between what would happen if we were controlling, instead of the pressure and the temperature and the density. Now the density is the order parameter for a liquid vapor transition. It's the macroscopic quality that distinguishes those two phases. And so by construction, it's a parameter which, if we tune, we can interpolate between the liquid and the vapor. Specifically, we know that there's a region at high density, which is what we mean by the liquid, a region at low density, which is what we mean by the vapor. And this region underneath this curve is a region of coexistence, whereby if we control the density to be somewhere underneath this curve, what we'll see there is a liquid in contact with its vapor. If we were to draw a picture, there would be some amount of liquid and some amount of vapor, and a surface, an interface separating the two. And that interface would be flat, because that would be the lowest free energy state associated with creating that interface, because, as we discussed last lecture, forming an interface is free energetically unfavorable. So a system will want to minimize the surface area associated with that interface, which in a macroscopic container is forming a flat interface. Now, if we control the density directly, what that means macroscopically is that, say, if we put ourselves here, it's not that the density homogeneously changes, it's just that in our little beaker, we have, in this case, less liquid at a constant density, this density here, than we do vapor, which is fixed at that density there. On the contrast, if we were to increase the density under that coexistence curve, all that would mean is not that, again, the density within the liquid or the vapor changes, it's just that we have more, in this case, liquid, than we have vapor in the right proportions to set that density to be what we want. Okay? So this is a reminder that, first, depending on what control parameters we're manipulating, be it the density or the pressure, we can access different macroscopic states. And the reason why then we don't see the liquid in contact with its vapor there is that we're not controlling the density, so we're giving the system the choice to decide what state it's going to access. And the state it's going to access is going to be the one with the lowest free energy, and the lowest free energy will necessarily not have an interface present. Whereas if we control the density, we don't give the system that choice. Okay, so that's some discussion of where we've been. A point which remains to be discussed in these phase diagrams is where this line ends. So you all know that in phase diagrams for typical substances that liquid vapor phase transition ends at a point. That point we've labeled before the critical point. What should we expect to see there? What does the system look like at that critical point? Well, let's think about manipulating the system by changing its density. So again, this coexistence curve tells us that as we get closer to this critical point, that the densities that the system likes to be in, either in its liquid state or its vapor state, let's redraw this. That as we increase the temperature, the density of the vapor gets closer to the density that the liquid likes to be in. Now, if we're underneath this curve, we'll still see an interface that separates the vapor from the liquid. But at higher and higher temperature, that density difference gets smaller. So the coexisting phases, in this case, liquid and vapor, become more and more similar. In fact, it's not hard to imagine that exactly at that critical point, there is no meaningful way to distinguish the liquid from its vapor. Those two phases are, for all intents and purposes, identical. So if the two phases become the same, what does that mean for what the system looks like? Well, the reason why the liquid separates away from the vapor and forms this interface we discussed before, the liquid enjoys energetic attractions that causes it to condense. The vapor enjoys a large entropy. That interface was unfavorable, but as those two phases become more and more similar, what do you think happens to the surface tension? Yeah, the surface tension goes to zero as we get close to the critical point. Gamma, which we've used to denote the surface tension, is going to go to zero exactly at the critical point. So what do you think the system looks like? It looks crazy, right? The free energetic penalty to form an interface is getting really, really small, which means interfaces can grow unbounded. What was a nice flat interface separating the liquid from its vapor can become rough and jagged. So maybe it would look something like this. Maybe I have big extended regions of liquid, big extended regions of vapor. And if there's no free energy penalty to pay for forming that interface, I can make that interface as big as I want. This turns out to be a very special state. Those interfaces are macroscopically large. And it turns out that there's a real, while it seems very complicated, in fact, the drawing, of course, looks kind of crazy, there is some real simplicity associated with that state that underlies why those interfaces look so large and extended, which we can get a sense of by comparing how the liquid vapor phase diagram changes as it approaches its critical point, and comparing that to how other similar sorts of phase diagrams look. So let's remind ourselves of a couple other phase transitions we've considered before. So if we had a fluid in the temperature density plane, that's the phase diagram we just drew. We have a vapor at low density, a liquid at high density, and a coexistence region between. Let's go ahead and define that critical temperature as Tc and the corresponding density as rho c. Now, another sort of phase transition, which we might consider, and we've talked a little bit about before, is a miscibility transition, or what we would see if we had a binary mixture, say between water and oil. So again, in the temperature, now mole fraction plane, mole fraction of oil, there is, in general, two phases. There's a oily phase at high mole fraction of oil. There's a wet phase at high mole fraction of water. and there's some coexistence region in between. And just like a liquid vapor phase transition, there is an end to that coexistence region where oil and water mix in all proportions. That has an associated critical temperature and now critical mole fraction. Indeed, these coexistence curves, at least the way I've drawn them, look similar. There's a little envelope which demarks those order parameter values as functions of temperature over which the system is in coexistence. Now, another sort of transition which has similar sorts of features, which we haven't talked a lot about, is that associated with magnetization. That's not one that's brought up in chemistry as much as it is in physics, but one could think about it in a similar sort of way. So a magnet the order parameter for a magnet is its magnetization. So a magnet, that's like your fidget spinners or your bar magnets that you might play with. You know that there is in general two directions that that magnet can point, up or down, which usually are denoted in permanent magnets by the little bars like that. It turns out if you put your fidget spinner in the microwave, it could lose that magnetization. So there's a temperature beyond which a bar magnet has no net magnetization. That temperature is also a critical temperature. Now the critical magnetization associated with that transition is just at 0 because that just says that beyond that temperature there is no net magnetization. So again, there's a region of coexistence that tells you I would have domains or regions in that magnet which are spin that are pointing up and pointing down. Now, if you just look at these curves, they all look kind of similar, but actually they can be measured with an amazing amount of accuracy. And the shapes of these curves, for example, can be measured, shapes of the coexistence curves. Near the critical temperature. And for example, if we were to measure for a whole host of different molecular fluids, water or ethanol, liquid argon, that if I ask for what the density of either the liquid or the vapor is relative to its critical density, as I approach the critical temperature, it approaches 0 as the temperature less the critical temperature to some power, and that power turns out to be very close to 1/3. That says that this region over here of this coexistence curve near the critical temperature as a function of temperature looks like, say that variation goes like rho to the cube, looks like a cubed power law. That's true for a whole host of different molecular fluids, insensitive to what the atoms and molecules that make up that fluid are, that near the critical temperature, that coexistence curve scales in the same way. Okay, so that's by itself kind of interesting. But if I look at mixtures, and I look at the mole fraction of one of the phases less than its critical temperature, critical composition, as I tune the critical temperature, well, that too can be measured. The shape of that coexistence curve can be traced out, and it too goes like a power of 0.0327, exactly the same as what you'd find for a molecular fluid undergoing a liquid vapor transition. But this is, of course, a very different sort of transition. This is a demixing transition, how water and oil mix, not how a fluid turns into its vapor. And yet, one observes similar sorts of behavior. What always blows my mind is if you were to do the same sort of experiment with a magnet and ask how does the net magnetization vary as that system approaches its critical temperature. Anyone want to guess what that power law is? It's exactly the same power law as what one measures for a mixture or for a liquid vapor transition. Now, these are incredibly different sorts of phase transitions on their faces. A magnet losing its magnetization, a mixture becoming miscible, a fluid turning into its vapor, and yet one finds quantitatively similar behavior for all of these different sorts of transitions. This is a phenomenon known as universality. Which is just defined as the same behavior for seemingly distinct systems. I think that really imparts how special that critical point must be, that independent of whether or not I'm looking at a liquid vapor transition or a magnet, the way the system behaves in the vicinity of that critical temperature is very similar. It's very universal. It's very independent of details. Now, we can get a sense for why a system exhibits universality by thinking about the heat capacity. If one was to measure the heat capacity, say per particle, as a function of temperature, for either of those systems, as I approach the critical temperature, what is observed is that while the heat capacity starts at low temperature at some finite value, as I approach the critical temperature, that heat capacity increases dramatically. Exactly at that critical temperature, the heat capacity, to the best of our ability to measure, is essentially infinite. The same is true as I approach that critical temperature from above. The heat capacity is observed to increase, and at the critical temperature it diverges. Again, this can be measured pretty quantitatively, and that heat capacity diverges at the critical temperature with some power that has some exponent associated with it. And that behavior too is the same for fluids undergoing liquid vapor transitions, for mixtures undergoing demixing transitions, and for magnets losing their magnetization. Now that is really peculiar. The heat capacity diverges, and the way it diverges, again, is insensitive to the molecular details. We've spent a lot of time talking about how we can understand the heat capacity and how it differs generically for different systems. In fact, one of the first things we learned when we thought about the heat capacity was how we should think about it microscopically. The heat capacity is related to what sort of quantity microscopically? Well, it's the energy fluctuations. If the heat capacity diverges, it must mean that those energy fluctuations diverge. That's very peculiar. How is it possible that the energy fluctuations can diverge? Let's work out a thought experiment where we take a macroscopic system and we divide it up into uncorrelated regions. So we take a little snapshot of our system, we grid up space into little boxes. Each one of those boxes has some extent, which is microscopic, but large enough that the fluctuations in one box are independent to the fluctuations in the other box. Let's imagine that there are m of those boxes, and then within each one of the boxes, there is some energy. That we'll say is epsilon. Say the energy in cell I is epsilon I. Okay, so if we wanted to, for example, compute the total energy of the system, well, I would just need to sum over all of the cells, the energy in those cells. And if all those cells are uncorrelated, you all know immediately what the mean squared fluctuations of the energy are going to be. What's just the number of cells times the mean squared fluctuations of one of the cells. That tells us immediately what the heat capacity is. Because we know the relationship between the heat capacity and the fluctuations in the energy. The heat capacity, say divided by the number of particles, is equal to a factor of kBT squared. The mean squared energy fluctuations, which is equal to the number of cells, times the fluctuations in one of those cells. Now, how is it possible for the heat capacity to diverge? Away from zero temperature, that factor of kBT squared does not diverge. M over N, well, that's a density, that's intensive. As I change the scale of the system, that does not diverge, it's just a number. And the mean squared fluctuations within one cell is something microscopic. That has no way of diverging. So the heat capacity written in this way contains no terms that can diverge. And yet, it is observed experimentally that at the critical temperature, the heat capacity does diverge. So what must be going on? It must be that we can't actually divide up the system in this way at the critical point. And more specifically, the reason why we can't divide the system up in this way is we can't separate out little regions which are uncorrelated from one another. So at TC, fluctuations are correlated. They must be correlated over macroscopic scales. It must be the case that each individual cell is so large that its fluctuations contain an infinite number of particles, or its volume contains an infinite number of particles, and if we have an infinite number of particles, then the mean squared fluctuations could indeed be infinite. And that's the only way to have a divergent heat capacity, is if the fluctuations become correlated over such large scales that we can't do this trick of separating out regions that are otherwise independent. So if we have fluctuations that are correlated over really large scales, well, that does sound very complicated, but there is also some chance for some simplicity, because if correlations extend over really large scales, then averaged behavior doesn't depend on what's happening locally, but rather what happens over those large regions of correlated fluctuations. So I average over large regions, so it's quite possible that the molecular details, the fine details, aren't so important for understanding this behavior. This might be why mixtures can act like fluids, can act like magnets, because the fluctuations are occurring over such large scales that any of those molecular details become unimportant. And so that's what we're going to try to do for the remainder of lecture, is introduce a simple model bereft of all molecular details that will nevertheless give us a lot of insight into what's happening. Let's introduce this model. So this model is known either as the lattice gas, or from the person who invented it, so-called Ising model. And it contains really the bare essentials for understanding something like a liquid-vapor transition. So what we envision is that we can grid up space into cells. Each one of those cells is maybe a little bit larger than a molecule. And in each cell, the density is either locally liquid-like, so there's a particle there, or locally vapor-like. So let me fill in some of these cells, which will be liquid-like cells, and leave some cells empty, which are going to be vapor-like cells. Let's go and label these. So that filled-in cell has a liquid-like density. Let's say that that was cell I, and we'll denote the liquid-like density with a variable n for cell I, which is 1. That's to be contrasted with this cell, which is empty, has a vapor-like density. Let's call that cell J. And we'll denote the vapor-like density with a variable which says that there are no particles in it and has a vapor-like density. We'll say that Nj is equal to 0. Now, we know that liquids form because of favorable interactions that bring molecules together, cause the density to increase. So we'll say that neighboring cells that are both liquid-like have an attractive energy minus epsilon. But that's only between liquid-like cells. That's meant to represent that if I have a molecule in one of those cells and another molecule in one of those cells, well, in general, they're going to interact with in some favorable way. And if those interactions are dispersive interactions, things like what one would imagine would be relevant for condensing methane or argon, those interactions are short range, so we imagine that the energy is only associated with attractive interactions between liquid-like cells that are neighbors. Okay, so that gives us sufficient information. Let's say that there are M cells. If we wanted to know, say, the total number of particles, well, I just need to sum over all the cells and ask if there was a particle, and if there's a particle there, that indicator function in I would return 1, otherwise it would return 0. So that gives me a convenient way of computing the number of particles. And from the rules I've just outlined, we can also write down the energy, which depends on if I have particle Ni and its neighbor Nj. If they are both liquid-like, if I multiply the two, I'll have a 1. If either of those are vapor-like, I'll get a 0. So I get a minus epsilon only if those products, the product of Ni and J, are both 1. And then I'll sum over I and J that are neighbors. And what I mean by that is, say in this plot, or in this graph, I look at only the 4 nearest neighbors that I share a side of a cell with. Now this is a microscopic system whose energy is fluctuating by the cell configurations changing, but also the number of particles are changing. If I, say, change one of those cells from liquid-like to vapor-like, I'm adding or removing a particle. That means the microstate of my system is determined both by an energy, which is fluctuating, and a number of particles, which are fluctuating. That's not exactly like the systems we've thought of before. So we have to generalize the way we've thought about probabilities of microstates a little bit. So let's imagine going all the way back to our isolated system where we arrived at our Boltzmann distribution to begin with. So again, this is some box which is rigid, so it keeps its shape, wrapped in insulation, so it keeps its energy, and impermeable. If I pull out a little part of that, I want to define as the system. The remainder is the bath. This model allows for exchange between the system and the bath of energy and number of particles. And when both are allowed to exchange, then the probability of my microstate has to be adapted. So the probability of a microstate we derived before, if just the energy can change, is proportional to e to the minus beta, the energy of that state. That came out from thinking about how the total numbers of states, which were all equally likely in the composite system plus bath world, reduced when I thought about just considering the microstate of that system. And essentially e to the minus beta, the energy of that state, was a way of bookkeeping the number of bath states commensurate with that system microstate. By analogy, if I allow the number of particles within the system to change, I need to worry about how many bath states there are that can accommodate the total number of particles being fixed. That should be something related to how the entropy of the bath changes with number of particles. So you should not be surprised to see that this probability now depends on the chemical potential, which is indeed how the entropy changes with number of particles. So the probability of a microstate in a case where both energy and material can be exchanged has both an e to the minus beta, the energy of that state, And the microstate also depends on how many particles there are. And so we have, in addition, in e to the beta mu, the number of particles in that state. So if cells were uncorrelated, how could we generate that? Well, that would be like setting the interactions between cells to 0. Then it's not so hard to compute the probability of there being a particle in one of those cells relative to there not being a particle in one of those cells. All of the cells are uncorrelated, so all I need to know is about what's happening in that cell, which is just a ratio of those microstates. I will end up with just e to the beta mu. That's just saying that there is no energy. The microstate of the system, if all the cells are uncorrelated, I just need to worry about what's happening in one of the cells. So the probability of there being a particle in this cell or no particle in that same cell depends only on that local number of particles. Thus, that ratio of probabilities is just given by the Boltzmann factor for that one cell. That implies immediately, from those binary operations you all have lots of experience with now, that the average number of particles can be written with that ratio of probabilities in a simple way. And it turns out that that goes like e to the minus beta, or e to the beta over 1 plus e to the beta mu, which at low density becomes just e to the beta mu. If we rearrange that, we find that mu is equal to kBt log the average occupancy. The average occupancy is just the density. And so this is a relationship we've seen before for an ideal gas. That there's a simple relationship between the chemical potential and the density. We'll derive this again more carefully at the end of the week when we move on to other questions of mass equilibrium, but it's convenient to see how it kind of comes out here. Now, if we don't have correlations, we aren't going to get that divergence in the heat capacity associated with a critical point. So in fact, we have to have interactions to see any of that correlated behavior. So with some finite epsilon. Now, if we want the probability of, say, cell I being occupied or being empty, well, there's a piece that has to do with that e to the beta mu, the change in the entropy of the bath as I change the particle number. But in addition, with those interactions turned on, now the energy change associated with Ni being 1 or 0 goes like beta epsilon now times some number of liquid-like neighbors. To compute the energy, I need to know what the neighbors of cell I are doing, whether or not they are liquid-like, in which case I get a favorable energy, or they're vapor-like, in which case I get no favorable energy. So this means that the statistics of Ni, of whether or not a given cell is filled or empty, depends on what all the other cells are doing. That's the essence of correlation, and that makes this computation very difficult. In order to understand how likely a given cell is to be filled or empty, I need to know well, whether or not the other cells are filled or empty. And to know whether or not the other cells are filled or empty, I need to know what their neighbors are doing. And so in general, this is very hard to solve. There does exist solutions in specific cases, but we're going to just allude to how one might tackle this. This is more complicated than anything I would ask you to do yourselves, but gives you a sense that by working through it, you know, that this model will have the kind of essential features to be able to describe critical points. So the kinds of approximations or analytical techniques one could use to make some traction into doing this calculation, some of you might have seen before in the context of quantum mechanics and many electron problems. One way to tackle this problem is using the so-called mean field approximation. In essence, it's going to say that the number of liquid-like neighbors for any given particle doesn't depend on what specific cell I'm looking at. I'll just concentrate on only one of those cells and average all the rest out. So it will be just given by the number of neighbors times the average of those cells. And in this square lattice we have up here, I have 4 nearest neighbors. So the number of liquid-like neighbors are just going to be 4 times the average number of cells that are liquid-like. And when I make that approximation, I can write down the average of cell I being occupied just as e to the beta mu plus 4 epsilon average of n over 1 plus e to the beta mu plus 4 epsilon average n. That still is an equation that has the average of ni over here on the left and the average of n's over on the right. So there's an additional constraint we impose, which again is like something you might have seen in your quantum mechanics classes, like in Hartree-Fock theory, which is that we demand self-consistency. Namely that cell I is just like all of the other cells. So the average of ni is just the average of n. So I have the average of n over here and the average of n over here. That is in principle a algebraic equation that I can solve. And get n as a function of epsilon and beta and mu. Again, this is a calculation which is hard to do. We won't go through the details of it. I won't expect you to be able to do this yourself, but in principle, one can do this within the mean field approximation. And what one gets out of this is the average n as a function of temperature does indeed have a critical point. It has a coexistence curve that is symmetric about 1/2 due to symmetry in this model. The critical temperature, so this 1/2 is essentially the critical density. And indeed, the critical density, the average density relative to the critical density depends on how close to the critical point one is, and it does so with a power. Anyone want to guess what that power is? It's kind of a bummer. It's not exactly 1/3. It's 1/2. So it doesn't give you what is observed experimentally. So there are 2 potential problems with this. One is that we've made some sort of error in doing a mean field approximation. or the model is inadequate. Somehow we've neglected important features of real systems that are not encoded in this model. So one of those two are true. So while mean field theory, the mean field approximation is about as good as we can get to trying to solve this equation analytically, there's an easier way to try to do that, and that is to use a computer to solve it. In fact, we could write up a simulation that encodes these rules, so sampling a Boltzmann distribution with that energy on a lattice, and we could just measure what the average density is as that computer simulation progresses. And indeed, what we find when one does that, so computer simulations can be made to study this model, essentially allowing us to compute these relationships how the average number of particles depends on t. And they give, when one does the computer simulation, essentially given the exact answer for this model, that the average occupancy less than 1/2 its critical density as a function of p minus tc goes like a power. Oh, but this power is 1/8. And again, not what I said it was a second ago. But actually, this is the right answer. This is what is observed in other two-dimensional systems. So you remember that we studied a demixing, or we showed some movies of a demixing experiment in a lipid membrane. If one traces out that coexistence curve for a binary mixture of lipids and a vesicle, one finds that the coexistence curve goes exactly like that power of the 1/8. So indeed, this model has the correct features for 2 dimensions. And if we simulate this for 3 dimensions, we find exactly the right critical exponents, this nearly 1/3 power. So in fact, this is a really good model. This Ising model or lattice gas has the essential features. It's just really hard to solve. This mean field theory, which is essentially the most sophisticated sort of theory one could present in this class. One could spend lots of time trying to develop more exotic theories, which are the subjects of graduate courses in statistical mechanics. But within the scope of what we can talk about, it's sufficient to say that it's hard to solve. Now, it is also worth noting that computer simulations could give a lot of insight into this problem. And so I've just stated that computer simulations can be constructed and they can be studied and they give you the right answers. It would be fun to actually then see what those look like. So let me try to make this a little clearer. It's t less than tc. So what I have done is I've written a computer simulation to study this lattice gas on a computer, and I've actually posted it to the web. So this is on a website that you can go yourself and play with. What I'm showing you here is an example of the simulation. It's at this URL. what I'm showing you here is blue, which are locally liquid-like regions, and yellow, locally vapor-like regions. Gotta have some Cal pride. This is a square lattice where I'm starting at a temperature below the critical temperature. And so if I allow this simulation to evolve, I see that on average, there is a flat interface separating the locally liquid-like regions from the locally vapor-like regions. Now, at finite temperature, there is some amount of liquid-like cells in the vapor, and there is some amount of vapor-like cells in the liquid. Now, as I increase the temperature, that interface disappears, reflecting the fact that as you approach the critical temperature, the surface tension goes to zero. And now those two phases, the liquid and the vapor, become completely miscible within each other. They completely mix. There's no meaningful distinction between the two. And what you find exactly at the critical temperature is what we anticipated, namely that there are tremendous amounts of fluctuations. If I look either in space or over in time, that the scale of fluctuations that I see are huge. I see all shapes and sizes of patterns emerging in this calculation. There are local liquid-like regions that are small in extent and large in extent. There are similarly sized regions for the vapor. This is a very complicated, correlated state of matter. And yet, because it is so correlated, a simple model like the Ising model is able to actually reproduce what is actually observed in complicated molecular fluids. Okay, so we'll pick up there next time. If you can't see this URL, I'll post it at the end of those notes so that you can go open it up and play with it yourself. Essentially, you have the ability of changing the temperature, of changing the composition, so how much liquid and vapor you start with, and how big the simulation is. So smaller simulations run a whole lot faster. Okay, that's all I got. Thank you for your attention.